pendulum. Okay, let's make, we have T2 0.6, 1.5, 0.4, T2 will be equal to 1.5, 0.4 divided by square root of 0.6. That's what we are having. That's what we are having. So, in this case, we are going to find the square root of 0.4. What will be the square root of 0.4? For 0.4, the square root will be equal to, we are having 0.632 divided by the square root of 0.6. For 0.6, we are going to have 0.74. If you try to multiply everything together, we are going to have the value 1.5 multiplied by 0.632, everything divided by 0.774. Then we are having 1.22 seconds, because we are looking for period, and the period is a time. So 1.22 seconds. And that is the solution to question number 33. Question number 34. A simple pendulum with a period of 2.0 seconds has its length doubled. Its new period is, this question we are still going to, the period is proportional to the square root of the length, and then we are still going to have, so that K will be equal to T for square root of, okay? In this case, we have a particular pendulum with a period of 2.0 has its length doubled. That means before we double the length, this is the original value. After the length has been doubled, we are still going to have, let's put it like this. For the first pendulum, before we double the length, the period is 2. 2 divided by the normal length is L. Simple. Which is equal to, what will now be the period of the same pendulum when the length is doubled. The length is doubled means you are going to have 2L. Okay? From here now, let's calculate the value of the period T1 or period T, or we can call it T1. T1 will now be equal to 2 square root of 2L divided by square root of L. This can be written as 2 times square root of 2 square root of L divided by square root of L. This cancels this. What we are having is 2 root 2. I know root 2 is 2 times 1.414. Will give us 2.828. Then seconds. 2.828 seconds. And that is what is being required. For question number 35, a boy timed 30 oscillations for a certain pendulum twice, that is in 3 times, and obtained the following records. We have 1 minute 10 seconds, that's for the first oscillation, 1 minute 12 seconds, and 1 minute 7 seconds respectively. The mean period of oscillation of the pendulum is, in this case we are to calculate the mean period of oscillation. So the period itself, what is period? Period is the total time taken to complete one oscillation. Period is total time taken to complete one oscillation, and is written as time for a particular oscillation over the number of oscillations. In this case, we are given different values. We have 1 minute 10 seconds for the first time, when we call it T1, is 10 minutes, 10 seconds. If you take this one to seconds, 1 minute is equivalent to 60 seconds. Sorry, this is 1 minute, not 10 minutes. 1 minute, 10 seconds. 1 minute is equivalent to 60 seconds. Plus 10 seconds, we have 70 seconds. Let's take T2. T2, we are given 1 minute, 12 seconds. 1 minute, 12 seconds. Okay, 1 minute is 60 seconds. Plus another 12 seconds. We are having 72. Let's take T3. We are given 1 minute, 7 seconds. 1 minute, 7 seconds. 1 minute is 60 seconds. We are going to have 67 seconds. These are the time to perform 30 oxidation. Because we are told the starting oxidation, which means our N is equal to what? 30. Okay? In this case now, the mean period of oxidation will now be equal to the mean period of oxidation, T, will now be equal to T over N. We are going to have 70 over 30 plus 72 over 30 plus 67 over 30, all divided by 3. Then what you are going to have here is this. What will be the value of 70 over 30, 70 over 30, 60 over 30? Okay? This can cancel this, or this, okay, sorry. This can cancel this, or we may not even cancel. Let's use our mathematical instrument to get the values out, so that we can get the actual value. We have 70 divided by 30. We are having 2.33 plus, then we have 72 divided by 30. We have 2.4 plus, then we have 67 divided by 30. We have 2.23, all divided by 3. And what I'm going to have now is everything together, 2.23 plus 2.4 plus 2.33. What we are having here is 6.96 divided by 3. And if you try to divide all by 3, we are going to have 2.32. And we are calculating for the mean period, which is seconds. And that is the solution to question number 35. Now we are moving to a new topic, and that is work, energy and power. Under this topic, the candidates are expected to know the following. Number 1, to be able to differentiate between work, energy and power. At the same time, to compare, they should be able to compare different forms of energy, then giving examples. Thirdly, they should be able to apply the principle of conservation of energy. They should also be able to examine the transformation between different forms of energy. They should be able to interpret the area under the force distance curve. And at the same time, finally, they should be able to solve numerical problems in work, energy and power. We are going to consider the following questions under this topic. Question number 1. Question number 1 says, an object of mass 50 kg is released from a height of 2 meters. Find the kinetic energy just before it strikes the ground. We are given the mass of the body to be equal to 50 kilogram. And we are given the height to be equal to 2 meters. We have to find the kinetic energy for the object reach the ground. And you remember that kinetic energy is equal to half mv squared. We are given the mass, we need velocity. Okay? We are going to consider from v squared is equal to u squared plus 2gh. By the time the object hops before it is being released, the initial velocity is equal to what? 0. U is equal to 0. Then we are going to have v squared is equal to 2gh. So that v squared is equal to 2 times 10 times 2. 2 times 2 is 4 times 10, which is equal to 40 meters. That v squared is equal to 40. So the kinetic energy will now be equal to half times the mass of the body, which is 50, then square your v squared, which is equal to 40. We are going to have 2 here, 1, 2 in 50, 25 times